Why is SEM resolution crucial for failure analysis? Imagine trying to solve a mystery where the clues are hidden in the tiniest details. That's exactly what failure analysis often feels like. When components break or fail, the secrets lie in microscopic features that are invisible to the naked. This is where scanning electron microscopy, or SEM, becomes an essential tool. SEM uses a focused beam of electrons to scan a sample's surface, creating detailed images of its topography and composition. The key is resolution, which tells us how small a feature the SEM can distinguish as separate. Think of it like trying to see tiny cracks or particles on a surface. If your resolution isn't high enough, those clues just blur together. High resolution in SEM is vital because many failure mechanisms happen at a nanometer scale. For example, fatigue failures often leave behind tiny surface striations that show how the material was stressed over time. These striations can be just a few nanometers wide, so you need a very sharp SEM to see them clearly. Without that clarity, it's like trying to read a faded print. Important details get lost. Fracture surfaces tell a story too. Whether a crack was brittle or ductile, or if it spread along grain boundaries, high-resolution images help identify these failure modes precisely. Microstructural defects such as tiny inclusions, voids, or precipitates can trigger failures. These features are often just a few nanometers across, so a high-resolution SEM combined with energy dispersive spectroscopy allows us to see and identify them. This helps pinpoint the root cause of the problem. Surface coatings or corrosion layers can be very thin, sometimes only a few nanometers thick. To examine these layers and small particles accurately, the SEM must have the resolution to distinguish such tiny features. Different SEM systems offer varying resolution capabilities. Tungsten filament SEMs might resolve features larger than 1 micron, but field emission SEMs can go down to a few nanometers. This flexibility allows analysts to choose the right tool based on the size of the failure features they are investigating. High-resolution imaging also supports other investigative techniques like fractography, which studies fracture surfaces, and elemental mapping, which shows the distribution of elements across a sample. These combined methods help reconstruct what caused the failure and how it happened. In the end, SEM resolution is the foundation of detailed failure analysis. It allows us to see the smallest clues that explain why a component broke or failed. Without high resolution, many of these critical details would remain as hidden, making it much harder to find the true cause of the problem. This clarity helps engineers improve designs, prevent future failures, and ensure products last longer.